Okay, it's a pleasure to be here. I'm very excited to be able to tell you all today about a new observable to look for Axion dark matter that we proposed, myself together with my supervisor, Asimina and our collaborator in New York, Ken van Tilburg. I'm assuming everybody here knows quite a bit about the Axion already, so I'll just summarize some relevant properties for this talk. When we're thinking about light bosonic dark matter, so in our galaxy, this is a massive less than about 1 electron volt, we enter a picture of convenience where it's more useful to think about this dark matter as being wave-like than particle-like, and it has the following properties: that locally it looks like a scalar wave, and its frequency is set by the mass of the Axion. It has an amplitude that's proportional to the square root of the dark matter density and inversely proportional to the mass of the particle. And there's also a small spread in its frequency, and this is set by the virial velocity of the dark matter in the galaxy, and it gives it a fractional line width of about 1 parts in 10 to the 6. Now I'll give you a preview of this new observable. So we'll be interested in this talk primarily in the Axion's coupling to the gluons, so the fundamental defining coupling of the QCD Axion. And the way our observable works is the following. If you take a piece of piezoelectric crystal, and in this piezoelectric crystal, it's required that you have some nuclear spins. Now, if you align these nuclear spins in the same direction using an external magnetic field, now, if we live in some background of QCD Axion dark matter, what you'll see is that, well, I don't know if you'll visually see it, but what would happen is that this crystal would undergo very, very tiny oscillations. This deformation, and it would have a periodicity that depends on the mass of the Axion. So how we'll describe this effect today. First of all, I'm going to discuss parity violations. So I'm going to talk about parity violation from two sources. The first being the parity violation that comes intrinsically from the structure of the piezoelectric crystal. And the second is the parity violation that comes from the Axion coupling to gluons. Next, I'm going to discuss Schiff's theorem, which tells us about the difficulty in detecting nuclear electric dipole moments and how we get around that. I'm going to talk about resonant mass detectors, and finally I'm going to discuss the proposed experimental setup and sensitivity to the piezoaxionic effect. So some background on piezoelectric crystals. Now, these are ubiquitous, so if you were to categorize crystals by their lattice structure, by the symmetry of their lattice, then actually 20 out of 32 possible symmetry groups are piezoelectric. Now, what this means in terms of its structure is that the positions of the ions in the lattice are breaking parity. And the result is the following: if you look at the figure on the right-hand side, that if you were to deform one of these crystals, you would have a net displacement of charge across the crystal. And what that means in practice is you have a crystal whereby if you deform it, you can produce a voltage across the crystal, and vice versa. If you apply a voltage to the crystal, it will cause it to deform. How can we understand this mathematically? So the equations that describe this are known as the constitutive equations. And they talk about how in a piezoelectric crystal, mechanical effects like a stress would be coupled to both an electric displacement and to a strain. Similarly, for the electric field, it could be produced by either a strain or an electric displacement. Now, what's special about piezoelectric crystals, we can understand in terms of symmetry. So here, the mechanical variables, so the stress and the strain, are parity even, whereas the electrical variables, the electric field, the electric displacement, are parity odd. And what's special about the piezoelectric crystal is that we know in order to produce something parity even from something parity odd, we need something odd times something odd to give us back something parity even. And that second source of oddness, the second source of parity oddness, it comes from the piezoelectric crystal. So in a crystal that's piezoelectric, we can couple electric fields to mechanical fields. Now, what happens when we add the Axion? So the Axion theta angle is not only parity odd, but it's also time reversal odd. And what that means is that we not only need piezoelectric crystal in order to produce a stress, which gives us our parity oddness, but we also need to polarize the nuclear spins in our crystal, because by polarizing all the nuclear spins in a certain direction, then we also introduce an additional source of time reversal oddness. So this tensor up here that directly produces a stress, we call the piezoaxionic tensor. But I should also point out that we can, using the Axion theta angle, produce an electric field directly using this electroaxionic tensor, which is in fact parity even. So to summarize that previous slide, the piezoaxionic tensor is odd under parity and can only be present in piezoelectric materials, whereas we could also have an electroaxionic tensor which would be even under parity and could be present in all dielectrics. But as you can tell from the title, I'm going to focus on the piezoaxionic effect. And that may seem odd at this stage, seeing as it seems that a larger class of materials would have an electroaxionic tensor. And I will hopefully confirm this to you at the end, that in fact the larger effect is the piezoaxionic effect, because that effect is resonantly enhanced. Now, how do we calculate our piezoaxionic and electroaxionic tensor? And this is going to require a journey from microscopic to macroscopic. So if we start with Axion dark matter, first of all, we think about how the Axion coupling to gluons will affect the properties of the nucleus. Next, we'll consider how by generating parity-violating moments of the nucleus, we can affect atomic electrons. In order to understand the piezoaxionic and electroaxionic tensors, we consider how this atom is embedded in a crystal. And finally, I'll talk about the readout for the system. So the first point I want to make is about Schiff's theorem. And so we know that the QCD axion should induce an oscillating neutron-electron dipole moment. However, it's quite difficult to measure this dipole moment in atomic systems. The reason being that if we treat an atom as a system of point particles, there's a theorem known as Schiff's theorem that says that the electric dipole moment would be perfectly shielded by the electron cloud. And how this works, if you look at the picture on the right-hand side, is that when the nucleus has a dipole moment in this limit of point particles and also the limit of it being static, the nucleus will move by just the right amount such that it exactly cancels out the overall dipole moment of the system. So how do we get around this? The resolution is known as Schiff's theorem, and it says that the relevant contribution in our case would be the fact that we need to take into account the finite size of the nucleus. And now the relevant multipole moment here is known as a Schiff moment. Now the Schiff moment grows with the size of your nucleus and the size of the nucleons in it. But in fact, there's two different sorts of ways you can produce a Schiff moment, depending on the shape of your nucleus. So the first scaling here, oh, I've lost my pointer, here, is for a spherical nucleus. However, there are these special nuclei, they're usually rare earth elements or possibly very heavy radioactive elements, but we're more interested in the stable ones, where there's an enhancement by a factor of a number of protons. And that enhancement is beyond the scope of this talk, but essentially depends on some kind of collective vibration of all the nucleons here in these intrinsically deformed nuclei. So now we've understood what the relevant potential of a nucleus looks like, this relevant parity-violating potential of the nucleus. We want to understand what happens when this nucleus exists within the lattice of a crystal, specifically a piezoelectric crystal. And now the potential our electrons feel will be the sum of both a crystal potential that's parity-violating due to the nature of the piezoelectric crystal, and a Schiff moment potential that's also parity-violating. Now what happens first of all, if you were to do this in perturbation theory, is that your crystal potential would mix S and P-like electrons. By S and P, I mean these hydrogen-like orbitals of definite parity and opposite parity in the ground state. So your ground state would no longer be a pure S-like orbital or a pure P-like orbital, but it would be a mixture of the two. And we note these admixtures by epsilon. And the result is that we get an energy shift that depends on the admixture, which comes from your piezoelectric crystal structure and your Schiff moment potential. Now, in order to understand the scaling of the piezoaxionic tensor, what happens here is that the piezoaxionic tensor depends on your Schiff moment potential and how that potential changes as you strain your crystal. And if you were to do this calculation, you would see that this would give us two parts. The first part that depends on your nuclear properties primarily, so on your Schiff moment, and the second part that depends only on your material properties, so on your admixture of S and P-like orbitals in your ground state. And this here we've calculated to be an order 1 factor. And the way we did this at the moment is it's actually related to the piezoelectric properties of the crystal. So we work from experimental values of the piezoelectric properties of the crystal. However, I should add that this is something that we would like to understand in more detail. So, how large a strain do we expect to get from this effect? So as an estimate, if you remember, it depends on our piezoaxionic tensor, it depends on our shift moment and our crystal structure, depends on the stiffness of our crystal, it depends on our nuclear spin direction, and here we expect this to be order 1, because we're going to very cool temperatures where we can polarize all the nuclear spins. Finally, it depends on our axion theta angle. And we've estimated this to be of the order of 10 to the minus 26, which sounds very, very small. However, it seems to be on the threshold of what we can already look for. So the idea of a resonant mass detector goes back to Weber, who invented these Weber bars to try and look for gravitational waves, and he did not reach the kinds of strains you needed to see a gravitational wave, unfortunately. But just to give you an idea of what this experiment is, here he had this very large aluminium bar when a gravitational wave passed through that would cause it to experience an oscillating stress that he would actually read out with a piezoelectric readout. And today we have experiments that are also looking for gravitational waves and also scalar dark matter. So an example here is the Auriga experiment. And they have already shown a sensitivity to scalar dark matter of the order of 10 to the minus 25. So it looks like we're about an order of magnitude away. So what's the experimental setup we're proposing? First of all, you need to find your ideal piezoelectric material. This would ideally have very low mechanical noise and big shift moments. Next, we want to align the nuclear spins in that material using magnetic field. We want to cool that to around a millikelvin to reduce thermal noise and also to make sure that all our nuclear spins are polarized. And finally, this is going to generate an oscillating voltage, and we would try to measure that using a readout involving a squid. So what would the potential backgrounds be in this experiment? So one of the primary ones would be fluctuating nuclear spins. However, we've calculated this and we believe it's actually a small effect. So one of the reasons this might surprise you, or not surprise you, one of the reasons for this is that the NMR frequency is not the same as the mechanical resonance frequency in our experiment, which tells us about the frequency of spin flips. And second of all, you could potentially have magnetic noise from fluctuating magnetic impurities. We found that these would not be relevant if you had less than parts per million, and in fact it's been demonstrated that you can grow crystals with magnetic impurities below parts per billion. So we think that's safe. Another source of backgrounds would be vibrational noise. This would be a systematic, and it's already been demonstrated at Auriga that you can mitigate for this, and examples would be seismic noise or human activity. Now, in terms of other noise, we're limited by thermal noise, mainly from the crystal, and we're also limited by noise from the squid. So what does an idealized forecast look like? So we believe that this setup could be used to probe axions between the masses of just over 10 to the minus 11 electron volts to 10 to the minus 7 electron volts. So that's frequencies of about 10 to the 5 hertz to 10 to the 8 hertz. Now, what we're showing here, so this yellow region is all of the potential parameter space that could be probed with this effect, assuming an integration period of a few years. The red and the blue here correspond to individual setups with a particular size of crystal. So in the blue region here, we have one crystal, and it would be sort of bar-shaped with its longest side around 40 centimeters long. Whereas for the red section here, we keep the same volume of crystal. We now have 128 crystals that are smaller. Their longest side is about 80 millimeters. The next thing to point out is that we have two lines here. This here is the electroaxionic effect, and this here is the piezoaxionic effect. And as I told you earlier, the reason we're more interested in the piezoaxionic effect is because it's enhanced on resonance. And that is what you see here with these little peaks. So what we're doing here is every time you hit one of either the fundamental frequency or one of its higher harmonics, you get one of these peaks. And we can scan around that by changing, to some extent, the electrical response of the system as we couple it externally to an additional inductor capacitor LC circuit, essentially. And yes, in order to fill in the rest of this yellow area, you would have to use crystals of different sizes or potentially come up with a new way of mechanical scanning. And now finally I should mention these two parameters here. This eta parameter corresponds to squid noise. So eta here equal to 1 would correspond to our squid being at the quantum limit, and 20 would be basically correspond to a squid noise temperature that's a factor of 20 above that. We can also probe the Axion electron coupling. So here I've written down the non-relativistic Hamiltonian for the Axion coupling to fermions. And now the first term here, the spatial gradient is P even and T odd. That's no good for us. We're interested in something that's P odd. However, the second term here is P odd and T even. And we can use that to directly couple to the electrons in our crystal. Now this has an additional advantage. Previously we had something that was T odd, so it required us to align our nuclear spins. In this case, seeing as we have something that's T even, we don't actually need to align electron spins, and we could even use materials that have unpaired electron spins. So future directions. The next things we need to do are we need to find precise shift moment calculations for more stable octapoldiform nuclei. Example of these are samarium, dysprosium, europium. We want to do a more involved density functional theory calculation for the piezoaxionic tensor and the electroaxionic tensor. So if you remember this material-dependent order 1 factor, we want to do further experimental investigation into suitable materials. And we also have an idea for an extension to this, which involves an Axion-mediated force experiment using a piezoelectric source. So this would actually probe an entirely different region of parameter space, so about 10 to the minus 3 to 10 to the minus 5 electron volts. And that will be in an upcoming paper. So in summary, we proposed a new observable for the QCD Axion that probes its model-independent coupling to gluons. It has an experimental setup with sensitivity to the Axion mass in the range of about 10 to the minus 11 to 10 to the minus 7 electron volts, and it's complementary to cavity experiments. Now, as I have a few minutes, I'll just go to my backup slide. So, I figured the first question people might ask is, what material do you have in mind for this setup? And it's not totally clear yet, but we believe there's a number of reasonable candidates at the moment. So when we're looking for a material, what we're thinking about is a high density of nuclei with large shift moments and low radioactivity. We don't want to heat up our experiment, and we don't want to hurt our experimentalists either. We want good acoustic properties, i.e. a high quality factor. We want strong piezoelectric properties because this tells us about, it's as you saw from that material-dependent factor, it relates to having a large piezoaxionic tensor. And finally, since we're dealing with materials that are not necessarily very well studied, it helps if they have some structural similarity to a material that we already use in bulk resonators, for example, something that had the same symmetry properties as quartz. And we didn't find a commercially manufactured material that satisfies all of these at the moment. However, there's a database at the Materials Project where you can categorize experimentally verified materials by their symmetry structure, their density, which nuclei they contain in them. And this is just a small subset of potential materials that we found that are similar to known crystals and have the right kind of nuclei in them. Okay, I think I'll stop there then.
The first question is material. The best material for that must be ferroelectric. I can see there the list. There are a lot of ferroelectric, but the clean ferroelectrics must be the best choice.
There's an issue with ferroelectrics, which is that because of its domain structure, it would probably have a very low quality factor. Not very low, but it would probably have a lower quality factor. It's better to find a piezoelectric crystal that's not ferroelectric. However, for our follow-up paper, we are necessarily considering ferroelectric materials.
But piezoelectricity is because of ferroelectricity. So
No, all ferroelectrics are piezoelectrics, but the opposite is not true.
I was working about 30 years ago. This exclusion got because it every time. How long it takes?
This one here?
Such a figure, how long it takes? Or will it take?
We're considering order of years, so I think this is a few years in this spot here.
1 year at least.
More than a year. A few years, yes.
And the other remark I will tell you, because somewhere you depend on the intensity of that matter, then you will hear the talk tomorrow from Abasa. I think you get productive afterwards.
Okay.
So I was wondering, you had half a million estimates as the office impurities.
Sorry?
Your estimates that office impurities was half a million. Yeah. Oh, sorry, fluctuating magnetic force. You just had it.
Yeah.
Fluctuating magnetic impurity. So your magnetic impurity density half a million. Where do you get that from?
Parts per million?
You said
We have the estimate in the paper, so we calculated at what level this would be a relevant noise source, and we found that at parts per million, below parts per million it would be irrelevant, and in fact we've seen that crystals have been demonstrated to be growing with less than parts per billion, so we don't think this would be dangerous.
I found that optimistic, but
It's very nice talk. The slide where you mentioned about the implementing this in an Axion force experiment, is this kind of like an Ariadne?
That is exactly what it is. So the idea is that we would take Ariadne and we would replace I think at the moment they use tungsten, we would replace the tungsten with a piezoelectric crystal, actually specifically a ferroelectric crystal. And yeah, in that case, what would happen is you could actually source Axions by the GG dual coupling off shell and create an Axion-mediated force.
Does this have any specific advantage over what Ariadne is?
So at the moment, Ariadne looks for this effective coupling to nucleons.
Is it a different coupling? Sorry.
Yes.
Yeah.
Yes, so my question is, I believe, is it paramagnetic impurities? I believe would be your problem. It's easy to get below parts per million paramagnetic impurities. We measure that all the time in crystals. Usually we get on the order of a few parts per billion, but it's very hard to get less than part per billion. And if you're less than part per million, I think it's probably okay. As from medically right crystals and measuring impurities, that's from my experience.
Okay, then please tell me more about that. Yeah.
Other questions?
So I think maybe you said in the end I missed it, but what's the current attack plan? Like you said, like you still don't have the material.
The current attack plan. Okay, let me go back to my slide. I think it was after this. Okay, so there are a number of things that we need to understand better. I'll say again. The first one is that our estimates of the shift moment could be done more precisely. We're actually thinking about that already. So a lot of the literature on shift moments, on these very large shift moments so far, has focused on radioactive elements. And ideally we want something that's stable or at least metastable. And so for those materials, an example would be, I think our favorite candidate in the paper was something like dysprosium. We need to do a more precise calculation. At the moment we're at about order of magnitude. The next thing we want to do is we want to understand a density functional theory calculation, so a numerical calculation of the crystal properties of this piezoelectric that will help us find a more accurate estimate for this order 1 tensor in the piezoaxionic and electroaxionic tensors. As we've just been talking about, we need to think more about the material. We want more experimental investigation into relevant materials. And then there's also this follow-up that we're writing at the moment about Axion-mediated forces.
Sorry, I meant more from the experimental point of view, because I seem like you want to probably not significantly change the kind of material you look for, in misunderstanding like.
So from an experimental perspective, I mean, other than investigation into materials,
Is some kind of
I think, for example, one thing that needs to be done would be thinking of a more, I think more work can be done to think about the scanning strategy. I suppose experimentally, I'm not the expert here, but the challenges would be getting this system to be very cool and developing a squid that would be very low noise.
Okay, one more question?
I'm on a very nice talk. Maybe you said this and I missed it, but are there any other ways of better experimental measurements of shift moments? Like, it sounds like you're trying to do all these calculations, but many of these are material science properties that, as a naive theorist, I might imagine there are other ways to go.
No, absolutely, people are looking for shift moments. I think one thing here is that we're looking for a shift moment that would be an oscillating effect. I don't know of other systems that look for an oscillating shift moment in the same range. So, but certainly there is a lot of work into looking for shift moments. If you look at an experiment that looks for neutron electric dipole moments, for example, an atomic system, I believe that what they're generally calculating is, since they can't directly probe the neutron electric dipole moment, what they would be doing is looking for the effect of the shift moment